every PCBs needs power supply for function to their operate. So as see also those power supplies should be provide stable current and stable voltage for our circuits. So also there are some sensitive components for voltages and currents. So then we need to ensure the protections for those sensitive components as well. So then there are some features. There should be some features of good power supplies, and those should be stable voltage regulation, and they should be ensure efficient power delivery to the circuit, and safe operation for every components for in the PCB. Yes. Okay. Yeah. So before going into the power supplies, I need to explain about two main regulation concept regarding this designing power supplies. First one is line regulation. That means line regulations means we should maintain constant output voltage when input voltage changing. Like in here in this figure, you can see when we can correct the constant voltage and we can get the constant output using this voltage regulator. But in here in this configuration, so if we change the input voltage, so we should get the same output voltage as the output, like when we change in the inputs, so we have to get the same output as previous. So that means like we call it as the line regulation. So we can some represent a equation. We can represent line regulation as the equation like ratio between input voltage change and output voltage change. So second concept is load regulation. So load regulation means so we need to maintain constant output voltage when load is changing. When load is changing means output current changing. So in here you can see there is a variable resistor connect to this one, and we connect the meter and voltmeter. So when we changing the resistance between this the load resistor, so that output current will be changed. So when output current will change, this voltage output voltage should be constant value when we changing the output current. So like that means we can call it as a load regulation. So we can represent that as a equation like ratio of difference between voltage with no load and voltage with full load, and we divided into P nominal voltage, and we get the load regulation. Yes, for that I'm hoping for classify if some criteria for classify this power supply. So based on conversion techniques, we can classify them as the linear power supply and switching mode power supply as well. So today I'm mainly hope to talk about this linear power supplies and switching mode power supplies, and also we can classify them as using based on their polarity. Polarity means so we can use them divide them as the single output power supply and dual output power supply. Like we consider single output power supply, like the normal batteries are single output power supply. So then when you consider dual output power supplies, so we can then as like two polarity power supply, then we can give the normal function generators, and normal, like in labs there are some power supplies, so that there we can get the plus voltages and minus voltages as well. So then they are considered as a dual output power supplies. Also based on isolation techniques, we can divide it into two categories, like isolated power supply and non-isolated power supplies. Yeah, those are the main classification categories. So today I'm going to talk about linear power supply block diagram and its working. So this is the main block diagram of linear power supplies. So this is the simple one. So here you can see this is the where we give the input, and this we give the get the output from that regulator. And this middle one is the regulator. So we use C, I, and CO capacitors for the smoothing parts for input and output powers. So yeah, so that's the main block diagram for linear power supply. And when we consider a linear voltage regulator, so this is the input like internal structure of that. So yeah, so there are many there are three main components. This transistor we consider then called as the pass element. Pass element means so that maintains the constant output voltage and controls the current flows between V in and V out. And this is the this op amp is working as the comparator circuit. So also there is a feedback circuit as well in the we can connect to the output terminal in that that's connected to the output circuit. Feedback circuit as a voltage divider. So that feedback is provided into this op amp, and it will compare with the reference voltage and give it to the output voltage according to that comparison. And according to that output, this transistor will change. The transistor output voltage will change. Then it will adjust the output voltage of the regulator. That's how it's working. So we can use this kind of capacitors for smoothing the input and output. So this one is working as the positive feedback circuit. So then we can derive the equation for output voltage like this. V out equals to V reference into 1 plus R1 over R2. Like that we can change this R1 and R2 values, and we can change the output voltage as well. Also there are some linear voltage regulators. Those have adjust pin in separate, like normal voltage regulators has 3 pins. So like some regulators have 4 pins regulators, like 1 pin for adjustable. So we can connect this kind of feedback circuit externally for that regulators. So as the example, so in the data sheets they are providing the minimal output current should be go through this voltage regulators. So according to that we can calculate this R1 and R2 values according to that and this using this equation. Yes. So when I move on to this switching mode power supplies, so maybe you are not heard about this converter, buck boost converters. So like we can convert that like this using this switching mode power supply. We can use the switching transistor for switch on and off, like control the input and output voltage using controlling the transistor. So we are using PWM signal for controlling transistor for that, and so we can using high frequency switching for like that. We normally use 25 kilohertz switching frequency for this kind of switching mode power supplies, and we can regulate output voltage, controlling this duty cycle of the PWM signal, and we can step up, step down, and invert the voltage cycle. We can use the buck converter for step down the output input voltage, and we can use boost converter for step up the output voltage, and we can use also buck boost converter for both scenarios like that. Yes. So this is the buck converter circuit. So this one is main configuration for buck converter circuit. Like in here you can see this is the control circuit for buck converter circuit. So in here this is the this controller provides the PWM signal. According to PWM signal, this transistor output will change. Like so if this PWM in on state, this transistor will on. So this will on, the currents go through this go through the inductor and this load and this path. And when the transistor goes to output off state, so this path will close. Like so then this inductor working as the magnetic field, like magnetic field to store the energy. Like it's working as the Lenz law. Like I think you know about that Lenz law. Like it tries to, when we off the transistor, it tries this current through this inductor is reduced. So it this inductor tries to keep the current in constant value. So then it will working as the voltage source again. So then it will again go through the current, this load, and this circuit through the diode will complete close. So then it will working the load, the current through the load is constant. Okay, so then we can provide the constant voltage using this kind of circuit. So we mainly use this for controlling duty cycle of the PWM signal. So we can derive the equation for output voltage using this T on time and T off time, and input voltage. This T on divided over T on plus T off means duty cycle. Like the duty cycle is on time ratio of on time over total time. Okay, so this is the equation for buck converter step down conversion. Okay. So then I'm going to boost converter. So this boost converter is step up the input voltage. Like we can get the high voltage as the output than the input. So it's as the same components is using as the buck converter, but the configuration is different. Like the transistor in here, transistor is here, but is then in this configuration, transistor is parallel to the this output capacitor. Like in this, we are controlling this transistor with the PWM signal. According to that, this output voltage will change. Like when if the transistor is off state, so current will go through this load. So if the transistor is on, this transistor is working as the short circuit. So then that circuit is closed, and also then this circuit capacitor is working as the voltage source, and it will provide the voltage supply for this load, and then we can supply constant voltage for this load. So then we can derive the output voltage equation for using duty cycle and input voltage like this. This D represent the duty cycle. So this so then we can get the like D is the less than one, so we can get the high voltage than the output way, because we divided the something with the less than one number, so we can get the increase the that we input voltage. Yes, so I will go through it the boost converter. So when you consider that, it's the different configuration that this inductor is middle of the circuit, like is parallel to the output capacitor. So then we can when we can control that also is using this PWM signal, and when PWM signal change, that will change the current go through path, though it will this inductor stores the energy as the magnetic field. So when the give the relevant power for this circuit, so that's the thing happened inside this switching mode power supply. So I think you can understand these things. So there is some comparison between linear power supplies and buck converters. So like we use LDO for like low drop voltage regulators for can regulate voltage smaller voltages. So we use buck converters for also, like we can get the more voltage gap between the input and output. So when we consider about complexity, the buck converter Yeah, this is the circuit for linear voltage regulator. So you can see I used two transistor here because of in here I didn't use op-amp circuit here. I only used transistor and zener diode for feedback circuit part. Voltage comparator part. So I used voltage divider for feedback. So when I run this, so we can see like the input voltage as the 12 volt, and we can get the output voltage as the nearly 10 volt, and it's the linear voltage. So when we provide the linear supply, so we can get the linear output voltage as the, so small, we can get the like small voltage difference like using this one. So I have the simulation for and uh, so this one is for Buckernut. Uh, Yeah, so in here I used this MOSFET transistor and this inductor for controlling this part, and also this PWM generator for connected to this MOSFET transistor. And when I run this circuit, so we can get this kind of output. So you can see if we measure this input voltage, that's shows the 12 volt input, and we measure the output. So that will there is some transient response because of this inductor and capacitor. So then the stable output voltage is 6 volt. So in here you can see there is some ripple voltage like some noise in here. So you can adjust this noise using by changing this capacitor. And also if we measure this current between this inductor, so you can like this exact level of current this goes through this goes to this inductor. So this that's the thing happen inside the inductor when we converting voltage using buck converter. Yes, that's the simulation for this buck converter using in the LT spice. Also I have the simulation is also this one for this simulation for boost converter. So yeah, boost converter. So like when I run this code, sorry, when I run this simulation, so you can see like the input voltage is nearly 5 volt, and when we measure the output voltage is nearly with 13 voltage, 13 volt. So there is a noise, high noise in this boost converter. So we can adjust this using using this adjusting this capacitor. And when you measure the current through this inductor, so that will very low variation than the input output voltage. So because that will happen in using in the this capacitors. So that's the simulation of this boost converter. So I think you can understand these things like it's simple. So we can get the more higher on input and output voltages difference with when we consider about when we considering about linear power supplies regarding the this switching mode power supplies. We can achieve the more higher gap between input and output. So that's the thing, main difference between these two things. And we can also transfer more power between these two. We can achieve more power using this switching mode power supply as well. And also if we want to convert this we are controlling motors with any other like let's say make a robot, we can control can use this buck and boost converters for changing voltages like slides voltage differences we can get using this buck converters also, other than using linear voltage regulators. So yeah, that's the thing I want to share with you.